Hey everyone, let's do a little video on the high side electrical switch. We want to turn on a load with a switch between the supply and the load. That's what we call a high side switch. We'll discuss that a little bit also. What is a high side switch? And most particularly, how can you do a high side switch? You can do one with a PNP BJT, or you can use a P-channel MOSFET, or you can even use a relay. Um, but then there's also some folks that like to use the N-channel FET as a high side switch, and that is not without some extra complication, but it's oftentimes worth it because the NFETs are higher performance than the PFETs. So I think on that note, why don't we just get started on approaches to doing high side switches? And it won't be super detailed here. It's kind of more of a architecture kind of thing as opposed to calculating resistor values. But or if we need to talk more, we can do that. We can do that in another video. Hello, everyone. Let's talk about high side switches. I guess first of all, we should talk about what do we mean by high side switch. So suppose we have a DC power supply here and a load, and we wish to turn the load on and off with the switch. And by high side switch, we mean just a switch that's in series with the high side or the non-grounded side of the power supply. Now, as opposed to a low side switch would be, suppose this was connected here, and then we broke this connection and put the switch in the ground leg of the load here, and then that would be what they would call a low side switch. So I want to talk about first what is a high side switch. We talked about that already, and then I want to kind of show some generic architectures for doing high side switches and some of the issues that people have with these architectures, and then suggest some alternatives that also are discussed. Okay, so what would the common ways of doing a high side switch? What are the common ways of doing a high side switch? One is a PNP bipolar junction transistor. So PNP BJT. And so what would that architecture look like? I'm not going to go into a tremendous amount of detail here, or this video will be 4 hours long, but the supply connects to the emitter of the PNP, the collector connects to the load, and then the base is where the control happens. Okay, so what are the goals here? What do you want? This is V supply. So for off, when your load's off, we want VB equal to VE. Now it doesn't have to be exactly equal to VE. It can be VB going to be a couple of VB can be a couple of tenths of a volt less than VE, and the BJT will still be off. But just as a quick, what would you like to see? So you don't have to think about it. If you let the base emitter voltage be 0, the part will be off for sure. And very often, this could be accomplished with a resistor here that pulls the base up to be equal to the emitter when you let go of this here. So you might put an NPN transistor down here, which turns this PNP on, and then when you turn that NPN off, a resistor here pulls the base up the emitter and then shuts the device off. So for off VB equal VE, that's not a real big issue, but for on, that's where the rub comes, in that we want VB is going to be approximately VE minus 0.7, but that doesn't tell you anything. Approximately, depending on temperature and how much current you're drawing and stuff like that. The rub comes in that IB needs to be, equal to, or maybe slightly greater than, approximately equal to, IC collector current divided by the SAT beta. All right. Now, because of the fact that we want this transistor to saturate, we want the collector voltage to come up as close to the emitter as we can. The collector base junction is no longer reverse bias. This is the collector here. This is the emitter. And this is the base. And the beta of the device degrades severely. So the SAT beta, what I would encourage people to use is a 10. So you can kind of see where the rub comes, and that suppose you got 10 amps of collector current, and your SAT beta is 10, then that suggests you need a whole amp of base current. Ouch. So problem. If IC equal 10 amps, IB needs to be about 1 amp, because SAT beta stands for saturation beta, approximately 10. Okay, so I think that's the problem. I think you can see the problem. It means that that you've got a fair amount of current, that fair amount of power wasted, and that current just basically goes to ground, doesn't do anything, and then you have a fair amount of power dissipation in this resistor here, and in the in maybe some in the NPN that's controlling this device. So that is the issue with the PNP BJT, and I think they make okay switches for low power stuff, but if you need 50 milliamps or something like that, if your load is 50 milliamps, if you want to turn on an LED or something, or string LEDs, you can do this. But for larger currents, I think it's kind of unwieldy to have 10, having a whole amp of base current be dealing with that. Now, the possible good side of the BJT is VCE SAT is 0.3 volts. That's generally what's used for VCE SAT. And that can be better than what you get with the MOSFET. MOSFETs don't have VCE SAT. They're different, but you can end up with more drop across the MOSFET fairly easily. However, with the BJT, you don't always get VCE SAT equal 0.3 either if you're not careful. For instance, do not use a 2N3904. So let me just start over again. VCE SAT can be 0.3 volts. That's not unreasonable to expect VCE SAT to be 0.3 volts, but don't expect VCE SAT equal 0.3 volts for a 2N3904 or 2N3906 in this case, because that's a PNP, at 100 milliamps. If you're running a small device like that at 100, near its maximum current capability, you won't be able to get really good VCE sat. So, and again, I think that pretty well states the problem. Um, and I would warn you also that if you build something like this, if you accidentally short this to ground while you're working on it, or one of your customers is working on it or working with it, that device will be blown before you can even realize what happened to it. They're pretty fragile, and if you put a fuse back here, the fuse won't blow fast enough to protect the device in most cases. And if you try to current protect these things, that can get quite complicated. Quite complicated. So I think that says enough about the PNP BJT as a high side switch. Now, what next? What's the next alternative? The P channel MOSFET. I think I might choose this. And here's the architecture. Again, you have your supply. You have your FET. This is the source. Arrow points out. This is a P channel FET. Here's the drain. Here's our load. And then we got our gate. And these are voltage controlled devices. Well, this is the gate. And they don't draw any steady state gate current. So if you turn on, or if you want this fed in this off state steady state or in the on state steady state, there's no gate current to deal with. Now you got to deal with some capacitance, some charge. You got to move some charge when you want it to change state. But in the steady state, no gate current. So that's the big plus. Big plus. There's no gate current. In a steady state. And how do we make these guys off? VGS equals 0 will work. You don't have to have VGS equals 0. You can have VGS equal to, and this gets a little bit tricky. This gets a little bit tricky. I'll give you an example here, just to show. So suppose this is a 24 volt supply. All right, and we got a P channel MOSFET with a threshold of -2 to -4. So this is just an example. Okay, example. If VT, V threshold, equal -2 to -4, that doesn't mean the gate voltage is negative. That just means the gate voltage needs to be 2 volts, or means the part will turn on when the gate is somewhere between 2 volts below the source and 4 volts below the source. So for this case, for off, we need VG greater than 22 volts. Okay, so that we don't accidentally have the part on when it's supposed to be off. But if you don't know any different, I mean, if you have VGS equals 0, the part will be off. But obviously, you could have the gate as low as 22 volts if your supply is 24, and then the part would be off if your threshold was -2 to -4. And you can see they vary, okay, a fair amount from part to part and over temperature, and so that would be a disadvantage maybe of the of the PFET. You need to swing some volts on the gate to make things happen. Now, what about for on? Okay, so for PFET on, what do we need to do to have the PFET be on? Well, the data sheet, I'll show you the data sheet in a minute. I'll show you a data sheet in a minute. The data sheet will specify VGS that and RDS on. That goes and an RDS on that goes with that. So for the PFET in the on state, you want to satisfy the requirement in the data sheet so that you can get the guaranteed RDS on that's in the data sheet. So example, suppose suppose RDS on equal 0.14 ohm, and this is what it's going to be for the data sheet I'm going to show you in a minute, for VGS equal minus 10 volts. Okay, now for our example on the previous page, with VS equal to V source of the FET equal to 24 volts, we need to have VG less than or equal to 14 volts. Okay, so VGS equal to minus 10 in this case. For VGS equal to minus 10 does not mean VG is negative. It just means it's 10 volt less than the source. So if our source is 24, our gate has to be 10 volts less than that to get the guaranteed RDS on. Not to turn the part on, but to get the guaranteed RDS on, we'd have to be 14 volts. Okay, so that's just a real quick overview of the two approaches that are most straightforward for high side switches, electronic high side switches. One is the PNP BJT, and the other is the P-channel MOSFET, and the arrow on the P-channel MOSFET points out. Okay, and then you got source, drain, and gate, and the gate is your control electrode, and you have to pull the gate down to turn the part on. Here you have to pull the base down to turn the part on. You have to pull current out of the base and pull the base down a little bit with respect to the emitter. It doesn't come down very much, only 0.7 of a volt, but you have to pull the base down to turn the part on. Here you pull the gate down to turn the part on. And the only thing is the gate's going to have to swing some volts, and you're going to have to pull out some charge to make that happen. So it can get difficult. You need to do it fast, but if you're turning a light bulb on and off, you probably don't care about that. Okay, so that is what I wanted to say about a couple of the high side approaches, electronic approaches. I don't think you should be ashamed to use a relay if a relay, note, let me just write here, note, relays are fine even today. I would venture to say most every car that rolls off the production line has a relay that turns on that electric fan out under the hood. All right, I won't guarantee that, but I would venture to say that they do. And if you use the relay as a high side switch, for instance, if this was a relay, what is a relay? Relay is a mechanical switch that's actuated by a solenoid. So you energize a coil, the coil generates a magnetic field, and that closes switch contact. So it's really it's an electromechanical device, not a single semiconductor in it. And this would be if you used a relay for this and accidentally shorted the load momentarily, let's say, it's likely, not guaranteed, that the relay would survive long enough to blow the fuse. Unlikely that this guy would survive if you shorted that node while it was on. Okay, relays are fine even today, and there are thousands of different kinds of relays: heavy duty, light duty, small, but you cannot duty cycle them. If you want a PWM, or if you want to try to do motor speed control or something like that, you cannot toggle a relay 1,000 times a second, or it won't last. Won't last an hour. They're not designed to. But if you want to turn something on and off every 10 minutes, a relay may last longer than the semiconductor equivalent, although they do have a finite lifetime. And so relays have finite switching, so finite number of switching switching events, or eventually the contacts wear out. In other words, so they can be considered maintenance events, maintenance items in some cases, and like in an automobile, they'll be socketed. You can pull the relay out and put in another one. A fuel pump relay in a car, another example. Turns the fuel pump on and off. So I don't know if the right term is switching events or whatever, but you wouldn't want to use one. Not good for PWM. You're trying to motor just to speed control the motor or something like that. You wouldn't want to use a relay for that. Toggle it 1,000 times a second. Okay. Okay. Picking back up again. Let's look at a real P-channel MOSFET. Vishay Siliconics IRF 9Z34. All right, so let's look at some of the things that we talked about just a few minutes ago. Let me hit the focus here. Try to get this thing to focus a little better. Gate source threshold voltage. This is where the part turns on. Notice for this particular part, it's -2 to -4 volts, like we had said. So, the worst case, if you want to be sure you're off, this is the one you want. Okay, you want to be sure you're off because it turns on somewhere between -2 and -4. So if you want to be sure you're off, you want to be closer to 0 than -2 is. So likewise, for the example that we talked about previously, this example right here, where we have the source at 24 volts, that means for the part we just looked at, this guy has got to be greater than 22 volts. So that's a little weird talking about having the voltage be greater to be sure it's off. But remember, we pull the gate down on a P-channel FET to turn the part on. So there's that. All right, now back to the data sheet again. So that's where the threshold comes into play. Now what else? The RDS on, where's that? Drain source on state resistance, RDS on, is specified as being maximum 0.14 ohm for VGS equal to minus 10 volts. So you don't have to have 10 volts to turn the FET on. You probably don't have to have minus 10 volts on the gate source to even get 0.14, but you do if you want guaranteed performance by the manufacturer. Okay, so minus 10 volts for RDS on of 0.14 ohm. That's what I meant by that. So again, back to the example that we were talking about before. If the source was 24 volts and you want VGS equal to minus 10, then their VG is 14 volts. All right. So how do you get that? If VGS is VG minus VS. So VGS equals to VGS, I should say, is equal to VG minus VS. So if minus 10, that's VGS requirement by the manufacturer, is equal to VG minus 24, well, I think you can see that if VG is 14, 14 minus 24 is minus 10. Okay, so VG equal to minus 10, and that is you can be minus 11, minus 12, that's fine. It doesn't matter, it doesn't do you any good probably, but it doesn't hurt anything if you're lower, if your gate voltage is lower than 14 volts, with the exception of this very fine spec right here, which would be your VGS max plus minus 20 volts. So absolute maximum ratings, do not violate these. Okay, your lifetime of your part may be in seconds if you do. So obviously for this part right here, you have to pull the gate down to 14 volts to guarantee RDS on, but you can't pull it all the way down to ground, because if you do, you'll have 24 volts across the gate source junction. Okay, so you have to keep this just little words to the wise on switches. Look at the absolute maximum ratings and do not violate those. They're not suggestions. They're usually, you're in real trouble if you violate them. Okay, so now, so what do we do with that? So suppose, this is just a note now on the relay here. So now suppose we have a motor that wants 15 amps. So that's a motor that wants 15 amps of current. So what does this mean for an RDS on equal 0.14 ohms? So what we would do is here's your resultant schematic in the on state, plus minus 24 volts, and your FET on resistance is 0.14 ohm. You get to replace the FET by a resistor of that value, and then your motor is here. And if this current is 15 amps, then you can go and do what you need to do with that and calculate that the drop across the FET, for instance, 15 amps times 0.14 times is 2.1 volts. So we're going to have plus minus 2.1 volts here. Worst case, because remember that's the absolute max over temperature and everything. Most of them, if you most parts, especially room temperature, maybe nowhere near that. It might be half of that. But the worst case over temperature, worst case part, 0.14 ohm. And so that would be 2.1 volts across the FET. And you have obviously not 24 volts across your motor, and your power dissipation in the FET is going to be I squared R. So P dis is this is 31.5 watts. So that is pretty bad. And so let's just see if that even makes sense or not. Personally, I think that kind of suggests we probably need to look for a part with a lower RDS on. And by the way, when you're looking at these data sheets, I mean, right on the very front cover, RDS on, right there, the 60 volts, minus 60 volt spec, and the RDS on, that's usually the things people need to know first, and they don't even make you wade through the data sheet to find them. Okay, so do we have a absolute maximum power dissipation here, or do we just so maximum power dissipation 88 watts. So it sounds like, wow, we're doing good here. We got lots of margin for power dissipation, but I think you might find that's at 25 degrees C, which what's running at 25 degrees C these days. So here is what what you would need to know here about when you're looking at that is how hot the part's going to run, because the maximum junction temperature is 175 C, I believe. I'm sorry, I'm going to have to go look at the front page on the data sheet again, see what the maximum junction temperature is. Operating junction, yeah, 175 C. That's pretty high. So what do we know? Look at this. If you run the thing junction to ambient, 62 degrees C per watt, there is no way that you can run the part without a heat sink with that kind of power dissipation, because that implies the junction, the temperature is going to be 62 times 32 watts hotter than the ambient, and that's too much. Can't do it. But with a heat sink, what do we know? We know our R theta case to sink and R theta junction to case are the following. And let me write these numbers down. So temperature. R theta, and then this is for the part we're looking at here now. This is the IRF 9Z34. Okay, so R theta CS case to sink equal 0.5 degrees C per watt, and R theta J to case equal 1.7 degrees C per watt. Okay, so this is a little bit like electrical stuff. They like to treat heat like electrical, like it's an electrical thing, and talk about resistances. And obviously, the more resistance you have, the more drop you get at it, depending on at a given current. And then likewise here, you can use these resistances and the amount of power dissipation you've got to calculate what the temperature delta is. So we have a thermal resistance from the junction in the part to the case of 1.7 degrees C per watt. And we have a thermal resistance from the case to the sink for a flat greased heat sink of 0.5 degrees C per watt. So we can add these two together and get an R theta J to HS, J to sink, equal to 2.2 degrees C per watt. And we know what our power dissipation is up here, 31.5 watts. So now we can calculate that 31.5 times 2.2 equals 69.3 degrees C, and that's your delta T. So what does this mean? This means that our junction temperature is going to be 69.3 degrees C hotter than the heat sink temperature. Okay, so if your heat sink temperature is 100 degrees C, you're getting pretty close to 175, aren't you? So that again, the fact that we've got 2.1 volts drop here across our FET, meaning that our load voltage won't be 24 anymore. It's like 22 volts. And we've got 31 watts dissipation in the FET. That's pretty high. And the fact that, if your heat sink is hot, and you say 100 degrees C, how could the heat sink be 100 degrees C? Heck, when I was working, the heat sinks were hotter than 100 degrees C. Everything is too small. Everything is too hot. That's the way it works. So again, this implies that the junction temperature is 69.3 higher than heat sink temperature. So you have to know what your heat sink temperature is. Now, how do you know what your heat sink temperature is? Well, we had mechanical engineers with degrees in this kind of stuff that ran modeling programs to try to predict what the temperature of the heat sink is, how big it is, what kind of thin area do you have any fans blowing on it, that kind of thing. But the goal is to keep the junction temperature less than the absolute max junction temperature with some margin if you expect the parts to last. Okay, so again, how do you find this? You find your total thermal resistance, which we were from junction to the case, that's the tab on the back of the part, 1.7, that's from the data sheet, and from case to sink, 0.5 degrees C watt per watt, that's kind of a standard thing for the TO220 package. So the total degrees C per watt from the junction to the sink is 2.2 degrees C per watt, and we multiply that by our watts, 31.5, and we get this kind of a temperature delta here. This is an important part of your design if you're designing anything that's going to go to a customer. All right, so there's that. All right, I'm going to pause again. Okay, picking back up again. We were looking at a PFET, P-channel MOSFET, IRF 9Z34, and calculating it had a maximum RDS on of 0.14 ohms, and we looked at an application where we had a 15 amp motor, and the power dissipation was 31 watts, which is pretty high. And the drop across the FET was like 2.1 volts, which is pretty high. And I would encourage you to be careful if you're working with big motors like that, because if you're having trouble with the run current, watch out for the start current, because the start current is liable to be 10 times the run current. And that will, especially imagine that you have a situation where something's mechanically wrong and the shaft on the motor is locked and the motor can't run. And so it's going to sit there and want 150 amps instead of 15 amps, and it'll vaporize your electronics unless you've been careful. So you probably need a bigger FET with lower RDS on, and then some kind of a current protection so that you don't vaporize stuff if the motor can't run because the shaft is locked, let's say. So you want a bigger MOSFET, do you? And that seems like a reasonable thing. The only thing is that you got to want to watch also is that right here, even for this particular part with this 0.14 ohm RDS on, we have a total gate charge of 34 nanocoulombs. All right, so that's the amount of charge pretty much that you have to take out and put back in when you switch. You know, in this case, you take that out when you turn the part on, and you put it back in when you shut the part off. Or I guess I had that reversed. When VGS is 0, there's you take charge out to pull the gate down to turn the part on. Okay, but anyway, you got 34 nanocoulombs there that come out. That the driver has to soak up when you do that. And you say, so what? Well, if you want to switch in 50 nanoseconds, which is a pretty reasonable time if you're doing a switching power supply, as you know, amps are coulombs per second. So if we just do the math here, we get that the gate current during the switching event is like 0.68 amps, which is pretty large. And so the bigger PFETs have a lower RDS on, but also a larger stored charge. So that's something to think about also. Now, other folks don't like PFETs because they are lower performance than NFETs. They'll have higher RDS on, and then if you go with a bigger part to try to get the RDS on back down, then you end up with more stored charge, and they're harder to get to switch. So can we use an NPN BJT or an N-channel FET as a high side switch? And again, because the NFET performs better than the PFET, and NPN BJTs also outperform PNP BJTs. I think most of the transistors people use in RF stuff and switching stuff are NPNs, not so much PNPs. But and then NFETs, outperform PFETs and are used more often in switching power converters, despite the complexity sometimes of using them. So how could we use an NPN BJT as a high side switch? Well, I'm going to cover up something for a minute. We have our supply, we have our load, and then somehow or another, this is an emitter follower. And hopefully you recognize that as an emitter follower. The output is on the emitter, and you have to put it this way because it's the way the current flows through an NPN BJT in the collector and out the emitter. So the load has to go down here. And maybe you see right away that the disadvantage of this is that I can pull that base all the way up to the supply voltage here, and the emitter is going to lag behind by 0.7 of a volt. And I can't do anything about that unless I can pull this base higher than the supply voltage. Well, how can I do that? Now, it's even a little bit worse than that, because how in the heck am I going to pull this base up close to the supply? Well, probably the best way to do it is with a PNP BJT, which you might be wondering, well, why didn't we just use the PNP BJT to drive the load directly? And that's an intelligent question. But so if we do the PNP BJT driving the NPN emitter follower, the best case is for the load voltage less than the V supply minus 1 volt. Where does that come from? I got a 0.3 volt VCE sat for this and a 0.7 volt VBE for this. So 0.3 plus 0.7 is 1, and this voltage can't get up any higher than 1 volt less than the supply voltage. So there's the disadvantage. Now, what's the advantage? Well, the advantage is this part isn't saturated. All right, and when it's not saturated, its beta will be higher, and that means it needs less base current. And the base current is not wasted current, because it just becomes part of the load current here. So that's a significant plus. And then the PNP, collector current, of course, is less. And that means I need even less PNP base current to turn this guy on and saturate him. So I mean, this looks pretty good in some respects, but holy smoke, can you live with a whole volt of drop? Now, before you say no one could ever be so crazy as to do something like that, I just want to show you this schematic of a part that some of you may be familiar with. It's this part right here, quadrupole half H driver. Okay, and so TI makes it, and so that's can be used for a motor driver. Not a real high spec motor driver, but a motor driver nonetheless. And I just want to show you the schematic of the output circuit, if I can find it. Here it is. And as you see, we have the very fine, there's your supply, and you've got your emitter follower driving the load, and a PNP pulling it up. So, on the integrated circuits, PNPs can be pretty weak. And that is the issue here. So this thing will handle an amp, I think. And so you can figure maybe this base current here is 10, 15 milliamps or so, assuming the beta of this part is reasonable, because it doesn't saturate again. And then this PNP only has to handle 15 milliamps, not the full load current. And a weak PNP can do that. So on an integrated circuit, sometimes the PNPs are really weak. Anyhow, so I just wanted to show you that you can use emitter follower as a high side switch at the cost of drop. All right, now what about using an MOSFET as a high side switch? So what about, we talked about the NPN BJT as a high side switch. Now what about the NFET as a HS, I'll abbreviate, switch? All right, so what would that look like? What would that look like? All right, so we got our supply, plus minus V supply. And then we're going to, we got our FET, and this is the drain, and this is the source. Arrow points in, here's the gate, and so we label these gate, drain, source, and then the load is going to be down here to ground. So this is an N-channel MOSFET configured as source follower. Okay, kind of like the emitter follower, only with a FET. All right, so what is the disadvantage here? So again, we're stuck. The highest you can pull this gate up to is the supply voltage. And because of the fact that there's no steady state gate current, it's reasonable that we could actually pull the gate all the way up to the supply voltage and have it stay there. So the highest we can pull gate is V supply. And then note that VGS equals VDS in that case, because the gate and the drain are both connected to the supply. So VGS is equal to VDS, obviously. And then I think you maybe, without even saying anymore, you see immediately that whatever the threshold voltage is, whatever the worst case threshold voltage is for this part, well, that is, we're going to need at least that much to turn the FET on. Because remember, we need VGS equals to, for instance, for some parts like 1 to 2 volts, let's say, to turn on an N-channel MOSFET. All right, and if the gate's at the supply voltage and VGS needs to be a positive number, that means the source has to be less than the supply voltage by at least, say, 1 to 2 volts in the worst case. And you use the worst case one, which would be 2 volts, and boy, that's pretty hard pill to swallow, and it's even worse than that. I want to show you here just for reference. I want to look at. So let me write down. Well, I'll show you this data sheet first. Here is the part. It's the IRLIZ34G, and it's a N-channel MOSFET. Okay, and here is the family of curves for that part. All right, so what are we looking at here? We got the drain source voltage on the x-axis and drain current on the y-axis. And unfortunately, they're logarithmic, so the curves don't look like they're supposed to look. And remember, VDS equals VGS. Okay, and so we're going to have to do a little iteration on the graph here. Here is 10 to 1, that's 10 amps. So this is 20 amps, that's 10 amps. 15 amps is going to be somewhere in there. And what kind of gate voltage? These curves here, all of these curves are for different gate voltages. So to be even up in this ballpark at all, we're going to be over here someplace. Right around here is where we're going to end up being. So we're going to need around 3.5 volts VGS, because that's the curve we're close to. And that also puts our VDS also around 3.5 volts. So you don't have to know exactly where you're going to be here, but I think you can see for sure that you're going to have your load. You're going to have a lot of drop. Okay, so for the IRLIZ 34G NFET, we'll need VGS equal 3.5 volts roughly for 15 amps. And so we're not even in the trial region. We're in the saturation region where those the curves are flat. So we're not in the ohmic region. RDS on, not applicable. And so what I'm point is it's a whole lot worse than just the fact that you got to have 2 volts to turn the part on. The threshold voltage on this part's 1 to 2 volts, but 2 volts won't cut it. You're going to need about 3.5 volts because we want 15 amps if you're trying to drive a motor, the 15 amp motor. So for if load is a 15 amp motor, then V load equal V supply minus 3.5. Okay, so I think that's just probably unacceptable. First of all, the power dissipation in this FET's going to be huge if that's 15 amps. I mean, that's darn near 50 watts power dissipation. 3.5 volts times 15 amps is that's over 50 watts. If your supply voltage is 14 volts, you will have 10.5 at the load, and I don't think that's acceptable either. Probably your motor is not going to run very well. So I think you can kind of see why this is even more unacceptable than the NPN emitter follower. Okay, and so this would be the big disadvantage here. Big disadvantage is I guess we'll just call this a disadvantage. Let's label this whole line here. Disadvantage. If the load is a 15 amp motor, the V load is V supply minus 3.5 volts, and that's unacceptable. Now you can fix that if you have another supply to pull this gate up maybe 5 volts higher than the supply voltage. If you have such a thing, another supply, and pull this gate up higher than V supply, this can work. But it's not simple, and it won't be fast if you have some little charge pump built into the package. That it's not going to be able to pull that gate up quick. But so it's probably unacceptable. But can be fixed with a higher supply. To pull gate higher than drain. Okay, and if you have a higher supply and it can give you enough gate current to be able to pull the gate up quick, and you have something that can pull it down quick, you can make a switcher out of it and do well. All right, but you have to solve that problem, and it's not simple. Not a simple thing. And so yes, you can use an channel FET as a high side switch, but you have to solve the problem of getting the gate up higher than the supply voltage, so you can turn the FET on all the way. Okay, and that's it. Hello everyone, picking back up again. Last time we discussed what happens if you try to use an NFET as a high side switch in the source follower configuration. And that would be what is shown here. This would be an NFET, arrow points in, that's an NFET, and this high side switch, the load's here, there's a supply 15 volts, and I've covered up some stuff, so just ignore that for the time being. And I think what we showed last time is for 20 amp NFET part, which we'll look at it again in just a minute, that if you pull the gate right up to the supply voltage, which is what you would want to do, you'd want to pull the gate right up to the supply voltage, that the source, if you had a 15 amp load, would want to be about 3.5 volts less than the gate to get this part to turn on enough to give you your 15 amps. So again, it's not just sufficient that you have VGS exceeding the threshold for the part. You have to turn it on pretty well to be able to get a lot of current through it, which you would if you were driving like a 15 amp motor, let's say. And I would say that is unacceptable, in that if this was 15 volts and that you only have 11.5 across your load, and you have more than 50 watts power dissipation in the FET, and basically just bad performance. Now, why would you even want to try to do that, to use an NFET as a high side switch? Well, here is why. The FET we looked at yesterday, we looked at two FETs. One, the PFET, this one, IRF9Z34, and then as the source follower high side switch, we looked at the IRLIZ34G NFET. Now, both of these are pretty similar parts, except for one's the PFET and the other's the NFET. This is a 20 amp part. This is a 18 amp part. The minus sign just means the current's coming out of the drain on the PFET. The current's going into the drain on the NFET. The QG, the gate capacitance, the charge that you have to pull out and push in when you turn the part on and off, 35 nanocoulombs versus 34 nanocoulombs. That's pretty much the same. The threshold voltage, VT, is 1 to 2 volts for the NFET, -2 to -4 for the PFET. Not the same, but not a big deal either. Now here is the big deal. Look at the RDS on for the NFET, 0.05 ohm at 5 volt VGS, and the PFET 0.14 ohm, 3 times as much almost, at -10 volt VGS. So this is the reason you might want to use an NFET instead of a PFET, because you get lower RDS on for the same size FET. Now, you can get PFETs with lower RDS on, certainly. And if you're driving a 15 amp load, I would suggest you get a PFET with a lower RDS on. Read the data sheet and see what you're putting in your circuit. Okay, common sense, I guess. But anyway, so that explains why we would want to use an NFET if possible, because they have higher performance than PFETs. They're faster, and lower RDS on. So now, what are some of the approaches people have come up with to be able to use NFETs here is a half H using 2 NFETs. And ordinarily, you might expect to see a PFET up here and an NFET here. And so here is 2 NFETs, and we're driving the load. And we have a supply, I just say 12 volts for this example. Now, this is from the datasheet for the IR2101, which is a gate driver IC. So that does not include these FETs, but it does include this stuff, the gate drivers. It's a gate driver IC, and it provides a gate drive for both the high FET and the low FET, separate circuits for that. And of course, you have to give it inputs to tell it what you want it to do. So gate driver, and driving these gates is a big deal. Inside this gate driver circuit right here is a PFET and an NFET. The PFET pulls up. They have this same circuit in here to drive the gates on these parts. A PFET to pull up and an NFET to pull down in each one of these. And that's because it takes pretty good current to, again, like we talked yesterday, if you want to switch these guys fast, you gotta deal with some current, and this IC can do that. All right, now how do they deal with the supply voltage problem and to get this part turned on good so that you don't have 3.5 volts drop across the FET when it's on? Well, they offer you the possibility of using a separate supply for this FET, and if you do, then that supply will solve your problem for you. Now, if you don't want to use a separate supply, they offer this, what they call a bootstrap thing. And again, this is from the datasheet for the IR2101 gate driver IC, and I just thought it'd be worth mentioning. Like, here's their circuit that generates a boosted supply. I call it a boosted supply, which they use to power the driver circuit for the high FET. And so consider here that what this circuit does, I'll tell you in words, is that it takes the AC here, because presumably this is some kind of a PWM application, motor driver speed control or whatever, and this is toggling, and so there's AC here, and so this capacitor samples that AC, and this diode halfway rectifies it. But you notice this diode is connected not to ground, but to the 12-volt supply. So this voltage will be higher than 12 volts here. And so if you want to see kind of why that is, consider when this is 0 volts, the capacitor will charge to 11.3 volts through this diode, because this is 12 volts here. So the capacitor will charge to 11.3 volts to this through the diode. And so this side would be 0 volts, this side would be 11.3. Now, when this FET turns off and this FET turns on, we have a pretty pathetic 11.3 volt supply here. So this part will start pulling up, and as soon as it does, this voltage will start to increase, and this will increase in lockstep with it. And so as soon as this voltage here starts to increase, this diode shuts off, and you'll see this voltage increase in lockstep with this voltage, and that provides the extra gate voltage to get this part to turn all the way on. And so that's what they call a bootstrap configuration. And it really is just a half-wave rectifier. Only thing is, the half-wave rectifier is not referenced to ground, it's referenced to whatever the supply is. So this voltage will be higher than the supply. In fact, it would be about 23 volts is what this would be. All right, it would be this 12 plus whatever the peak-to-peak swing is here, which would be about 12 volts also. So 23 volts roughly here, and so this circuit would have to have some kind of a limit so that you didn't damage the gate source junction of this FET. But that solves the problem of, and I believe this probably works. I haven't ever tested it myself, but again, it's in the data sheet for the IR 2101, and I thought I would just explain how it works, um, so so make more sense to you. Okay. Now, suppose you just want to use an NFET to turn on a load, on and off, maybe once every 10 minutes or once every hour or something like that, and you don't have an AC source here that you can steal some of to build this little power supply. Because really, that's what we're doing. We're building another power supply. If you happen to have another power supply, you can use it, and it's higher than 12 volts. Let's say for this application, if you happen to have a 20 volt power supply, hey, you could use that, and then you're good to go. But presuming you don't, then you can use this little circuit to generate a boosted supply for your high gate driver. Now, suppose you have something like this, however, where this is not toggling. This is just kind of an on-off thing. And now what would you do? Well, I haven't built this circuit and tested it, but you could conceivably, if you have, say, a 5-volt logic device, let's say, you could take one of the outputs from that logic device and use that to, turn your FET on and off. So, for instance, you turn this device on with a high here, and that pulls this down and shuts this FET off when you want the load off. And then when you want the load on, you turn this FET, this BJT here off with a logic low here, and then this resistor can pull the gate up to whatever the supply is. Only in this case, with those two diodes, there would be supply minus 1.4, which would make it even worse. But if you were to have another output on this very same FPGA outputting, say, a 5-volt square wave, 0 volts, 5 volts, 0 volts, 5 volts, 0 volts, then we end up doing the same thing as what they did up here with the little bootstrap circuit. So basically, when this is 0 volts here, this capacitor is going to charge to 14.3 volts. So it'd be 0 volts on this side, 14.3 volts on this side. And then when this jumps up to 5, this would jump up to 19.3. You jump from 14.3 to 19.3. So that's what the waveform would look like, 14.3 to 19.3 here. And then this diode just rectifies that so that you'd have like 18.6 volts here. And you might or might not want a little capacitor here to hold that, but maybe remember this device is going to be off, out of the picture, and the gate source capacitance here of this part may hold that voltage good enough that you don't even need to worry about it. Now the question is 18.6 volts high enough to turn this part on? It's 3.6 volts higher than 15, and that wouldn't get you the guaranteed RDS on, but it might be good enough, and that's about as good as you're going to get if you have a 5-volt logic device here. Maybe if you use Schottky diodes here, you could do a little better because they only have like a 0.35 volt turn on. But realistically, if you need 20 volts or more here to be sure this guy is turned on really good, you're going to have to buffer this with a little inverter, a little BJT inverter circuit, so that you can have, instead of 5 volts peak to peak here, you can have 15 volts peak to peak. And now you rectify that, and then you have to put a Zener diode in there or something so you don't damage your gate source junction on your FET, and you're building another supply. And it doesn't have to be a great supply, but you're building another supply here just to turn this part on really good. So that's the cost of using an NFET as a high side switch. Okay, and so that's it for this. Hey everyone, let's conclude this here with just a very, very quick overview. So what did we talk about in this video? First of all, what is a high side switch? Then the standard approaches for high side switching, which would be the PNP BJT and the P-channel MOSFET, and then possibly a relay. In some conditions, relay is very acceptable in my opinion, but certainly not at all. And but the PNP device has, I would say, almost showstopper issues if you have high currents involved, in that it needs a lot of base current. So that's a real disadvantage for the PNP high side switch. The PFET, P-channel MOSFET, is better as a high side switch in that it does not need steady state gate current, so that's a plus. And we talked about the gate charge a little bit. If you do need to switch a FET fast, then you want to be thinking about how much charge you have to push in and take out every time it switches, and that determines what kind of a gate drive circuit that you need. And you talked about that briefly, and again, that's one of the specs that you see in your data sheet. And then we considered a couple of maybe less common or less straightforward approaches to high side switching. One would be the NPN emitter follower, and that has issue with drop. You're not going to be able to pull your load voltage all the way up to the supply voltage with that. About the best you're going to do is 1 volt drop. And then the N-channel MOSFET as a source follower is even worse. Maybe you might have as much as 3.5 volts of drop between the source voltage and your load voltage if you just try to use a simple NFET as a source follower. But there's a fix for the source follower if you boost the supply voltage a little bit. So we talked about that. So that's what we talked about. And if if you don't remember going over some of that stuff, maybe look back in the video again. But that's what we tried to talk about, at least. So I thank you for watching, and we'll catch you in the next video.